Welcome, ladies and gentlemen, to Chapter 1 of the course Linear Algebra in 2D. We will be talking about coordinates and vectors in this video. Now, the two sections of this short videos will be coordinates and vectors as the title, and then I will briefly talk about the norm of a vector. First, we look at coordinates and how vectors are made up from coordinate systems. So historically, geometry was based on constructions using ruler and compass, which you've probably learned to do in school. And only with the introduction of Cartesian coordinates by René Descartes in the 17th century, it was possible to algebraically describe geometric objects. Now, how does this work? We have our plane here, where the points in the plane live, and we can use two numbers to describe every point uniquely. For this, we need a coordinate system, so we have two axes here. In this case, these axes are orthogonal, so usually we draw the axes to be orthogonal. We have the point where the two axes meet. This is our origin, and to this we assign the coordinates 0, 0. And then for any point, here we call this point x, for any point in the plane, we assign two coordinates to it, namely x1 and x2, where x1 is the distance we have to go along the first axis, and x2 is the distance we have to go along or parallel to the second axis in order to precisely reach our point x. And with these two numbers we can uniquely identify any point in the plane, and so we obtain our coordinates to describe points in the plane. And for better visualization, or if we actually want to indicate that we have some kind of direction going on, we often represent a point in the plane by an arrow emanating from the origin with coordinates 0, 0, and then we draw this arrow from the origin to our point x. And with this point of view, we consider the point x to be a vector. And our two coordinates, x1 and x2, are called the components or the coefficients of the vector x. The origin is also called the null vector. So in this vector notation, we usually write them one above the other. And note that I don't use a special symbol for the null vector. I just use the ordinary 0. And it will be clear from the context whether I'm speaking of the number 0 as it appears in the coefficients here, or the null vector. And a remark on the notation. So you might be used to vectors being denoted in some special font. For example, you will find some really ugly things like having x with an underline, or in some very old texts you might find vectors being denoted by Gothic letters, or in more recent texts often you use boldface, or you use a little arrow over the letter x to indicate that it is a vector. I will not do this in this course because vectors are the central objects of this course, and it's quite usual in linear algebra courses to not use a special font to indicate vectors for this very reason. So you have to live with the fact that vectors are just written in the same font as normal numbers. Now, what can we do with vectors? We can apply some algebraic operations to them in a very intuitive manner. For example, we can add vectors. What we do here is we have two vectors, x and y, given as arrows, and we just take the one vector, say y, and we glue it. We glue the base of the vector to the tip of the other one, and wherever that points then, this is the addition of the vectors x and y. So we take y, glue it to the tip of vector x, and then the tip of y glued to x points to x plus y. And algebraically, this is the same as simply adding the components of the two vectors. So in each coordinate, we add the respective entries in the vector. So x plus y, if we write it as x1, x2, and if we write y as y1, y2, then x plus y is x1 plus y1 and x2 plus y2. So it's clear from this algebraic representation that the addition of vectors is commutative. That means it does not depend on the order of the vectors. So x plus y is the same as y plus x, as we can see from the component-wise addition, because here we just add some numbers, and for those numbers, addition is commutative, so we can just reverse the order. And geometrically, this means if we take y and glue it to the tip of x, or if we take x and glue it to the tip of y, then either way we will end up at the same vector x plus y or y plus x in the plane. Another operation we can perform on vectors is multiplying it by numbers. So we can stretch or shrink a vector along its own direction by multiplying it component-wise by a number lambda. So if lambda has a negative sign, then this causes a reflection about the origin. So for example, here we have our vector x again. And here, for example, I take lambda equal to 2, so I multiply x by 2. And I do this by multiplying each component by 2. And the effect is that I just stretch the vector x by a factor 2. So I get a vector that points in exactly the same direction, but has twice the length. Or what I do here, I multiply x by minus 1/2, meaning each component of x is multiplied by minus 1/2. And so this, first of all, shrinks the vector x to half its length, but also flips the orientation. So we point in the opposite direction as x did originally. And in vector calculus, it is customary to call the numbers that we use to multiply vectors as scalars. So that's a term you should be familiar with, and I will be using it in this course. We can form so-called linear combinations. So this is the following. Any vector x is, as we already observed, uniquely determined by its two coordinates x1 and x2. So we can uniquely represent x as a sum of the following form. So here we have the two coordinates x1, x2. And this is the same as writing x1 times 1 over 0 plus x2 times 0 over 1. And these two vectors here, we give the names e1 and e2. And together, we call these two vectors the canonical basis. So this canonical basis forms a coordinate system. And with respect to this coordinate system, the two entries of our vector are the coordinates. And the sum of this form here is called a linear combination of the two vectors e1 and e2 with the coefficients x1, x2. And we can take linear combinations of vectors that are not just the two canonical basis vectors. So we can take arbitrary vectors x and y and form linear combinations of them. So that's just a combination of the vector addition and the scalar multiplication. For example, if we have two scalars, lambda and mu, we can form the linear combination lambda times x plus mu times y. If we write it out in coordinates, that's lambda times x1, x2 plus mu times y1, y2. So we multiply those two each by lambda and those two each by mu. And then we combine them by adding them component-wise. So this linear combination lambda x plus mu y is the vector with components lambda x1 plus mu y1 and lambda x2 plus mu y2. Geometrically, we have an example here. So we have our vector x and our vector y again. Now I take 1/2 times x and then take minus 2 times y. And yeah, I can add them in the usual way by taking 1/2 times x and gluing it to -2 times y, and we end up with the vector here, which has these coordinate entries. And we will revisit linear combinations in a later chapter because they are quite important when we want to change coordinate systems. Now for every vector x, we have a vector -x, which is just its reflection about the origin. So this means if we add x to -x, we get the null vector, the origin. And yeah, it's pretty obvious how that is viewed geometrically. So if this is x, then -x is simply the vector with the negative coefficients, the one that is obtained by flipping x about the origin. And vector addition is also associative, essentially because the addition of the individual components in the vector is associative. So geometrically, we can visualize this as follows. So we have 3 vectors here, x, y, z. And if we first add x plus y, so corresponding to this term here, and then after taking this sum, we add the vector z to it. That is the same as if we first add y plus z, so corresponding to this term here, and then add x, so we take this vector here and add it to this one, and we end up at exactly the same vector in the end. So if we have parentheses in a vector sum, we can just move them around. There's also a distributivity law for vector addition and scalar multiplication, which states that if you have a scalar lambda and 2 vectors x, y, then lambda times the sum of x and y is the same as the sum of lambda times x and lambda times y. And this is actually a theorem from elementary geometry, which is called the intercept theorem. So if we look at this, we have x, we have y, and then we have x plus y. So together, these 3 vectors form a triangle. And if we now take lambda times x, and we take lambda times y, and we add them together, then we get lambda times x plus y. So we get a vector that's on the same arrow here. And this one, because it's a multiple of y, is clearly parallel to that one. They point in the same direction, as we can see here. And now this intercept theorem states that the ratio of this side of the triangle to this side of the triangle is the same as the ratio of this side of the blue triangle to this side of the blue triangle, because these parts here are parallel. Yeah, and of course the ratios are just given by the length of x divided by the length of y, or the length of lambda x divided by the length of lambda y, and the lambda of course cancels out, so you see the ratios are the same. And this is represented by this distributivity. Now, the norm of a vector is just the length of it. So it's a geometric property, but it's customary to not speak of the length of a vector, but to speak of the norm of a vector. And the notation that we use are these double bars that are reminiscent of absolute value bars, but for vectors we use double bars. And yeah, we can simply deduce this by the theorem of Pythagoras. So we have a vector x here, and the norm is the length of this vector. And we have the 2 coordinates x1 and x2. So if we go along x1 and then orthogonally to that along x2, then we have 2 side lengths of a right-angled triangle. So we have a right angle here. And this allows us to deduce a value for the length or the norm of x. So yeah, the leg length, as I said, are x1 and x2. And the hypotenuse is the vector x in this triangle. So the length of the hypotenuse is just the norm of x. And Pythagoras, the classical theorem for right-angled triangles, says a squared plus b squared equals c squared. So c squared would be the square of the norm. A and b would be these two coordinates here. So norm squared equals x1 squared plus x2 squared. Or if we take the root, then the norm of x is just the square root of x1 squared plus x2 squared. And some important properties of the norm are as follows. So if we have two vectors x, y and any scalar lambda, then the following holds. The norm is always greater or equal to 0, and it is 0 precisely if x is the 0 vector. So any non-zero vector has a positive length. Now the norm of the multiple of a vector is the same as the norm of the vector multiplied by the absolute value of this scalar that we take for the multiple. And then we have the so-called triangle inequality. So then if we have two vectors x and y and we take the sum x plus y, then the norm of the sum is less or equal to the sum of the individual norms. So norm of x plus y less or equal to norm of x plus norm of y. And here we have equality if and only if x and y point in the same direction. So x and y are multiples of each other. So there's some scalar that we can multiply one of them with, say, y in this case, so that we get x. And we can prove this. Now for the first part, recall that the norm is defined to be the square root of x1 squared plus x2 squared. And well, here we add two numbers that are greater or equal to 0. And if we take the square root, it's still greater or equal to 0. And we get 0 under the square root precisely if these two summands here are both 0. And yeah, the square of a number is 0 if and only if the number itself is 0. So here we get equal to 0 if and only if both of the coordinates are 0 themselves. So this means x is the 0 vector. Now we take the multiple of a vector x and look at the norm. So if we write this out explicitly, then lambda times x is the vector with coordinates lambda x1, lambda x2. This is the square root of lambda x1 squared plus lambda x2 squared. Now we can factor out lambda squared from this one. So this is the square root of lambda squared times x1 squared plus x2 squared. Again, we can take the lambda squared out of the square root. So this is the square root of lambda squared times square root of x1 squared plus x2 squared. And what happens here, we have any number lambda, we square it and take the square root. So by squaring it, we forget whether it's a positive or a negative number. And then taking the square root, which has to be positive, we end up with the absolute value of lambda. And this part here, of course, is just the norm of x. So we have lambda absolute value times norm of x. And for this triangle inequality, I'm a bit lazy and just draw this picture here to indicate how this works. So if we have x and y and we add them, then we get this vector here. And from elementary geometry, we know that going from here to here and then from here to here is a longer path than just going the straight line from here to here. And only if x and y were to point in the same direction, we would have that the length of the two just add up for the length of this segment here. Yeah, and that's it about the norm. And I'm at the end of this video. Please like this video and subscribe to my channel to help me produce more great content for your enjoyment in the future. And also, if it's not too much to ask, please watch my videos to the end, because that is good for the YouTube algorithm.